In this video, we're going to look at the simple kinetic molecular model, and in particular, the syllabus points down here. First of all, what is the simple kinetic molecular model? It sounds far from simple given its long name. Well, kinetic refers to the fact it considers moving particles, and basically what we do is we consider properties that we see, for example, pressure, temperature, in terms of the molecules that make them up. We consider those just to be spherical, hard objects. Consider them a bit like marbles or something like that. And by thinking about how they are arranged and how they move, we can use this simple kinetic molecular model to explain things we see. So when we see that model, all it means is we're considering the molecules as round circular balls, and there's some other considerations and assumptions we make, but basically these balls move around and they move differently depending on whether it's a gas, a liquid or solid. Start with this syllabus point here. Explain pressure in terms of change of momentum. Well, hopefully you remember what causes pressure. This involves particles. So this is a gas here I'm drawing. I'm drawing the circles to represent the molecules and the lines represent the fact that they're moving quickly. What causes pressure is that when these particles collide with the walls, and you always need to refer to that, it's not just when they're moving and colliding with each other, it's when they collide with the walls of the container. So collide, two key words there. When they collide with the walls of the container, they exert a force. Now, why do they exert this force? Well, it's to do with momentum. At the first stage, the molecule is moving in that direction with a velocity. And if you remember, momentum is mass times velocity. When they hit the wall, they bounce off and they travel in an opposite direction. So here's the particle a bit of time later. But you can see, remember that velocity has direction. And because the direction has now changed, that means there's been a change in momentum because there's been a change in direction. So as it collides, there's a change in momentum, which is a change due to the change in direction. Well, hopefully you remember that there's an equation that tells you that force equals change in momentum over time taken. So the fact that there's a change in momentum because there's a change in direction when they collide tells us that there's going to be a force exerted on the wall. And that force is acting on a wall. And if you remember, pressure equals force over area. Now I know it's a bit confusing here. We've got capital P for pressure here, and we've also got P here for momentum. But this is pressure, this one. And because there's a force acting on an area, we have a pressure. And that's what creates pressure. So that's what this syllabus statement here refers to. These ones down here are all to do with Brownian motion. Now, what is that? Well, this goes back a while to a scientist called Brown, where his surname was Brown, and he looked at pollen in water. Sounds dull, but was actually really interesting. What he noticed was pollen, which is quite a big molecule, was moving around with a random jerky motion like that. It can also be observed if you put smoke under a microscope and put it in air, and you'll see that the smoke particles move around with a random sort of jerky motion. And he wanted to explain this. Well, one way to explain it, and this helps prove the idea behind the simple kinetic molecular model, is that there are loads of little particles. So I'll draw these with red dots here. So if we zoom in on this, what's going on? Let's have a look. Well, there are loads of little air or water, if it's the pollen grain, particles. The big smoke particle looks something like this. Now remember, if we consider that they're all moving, this is the kinetic model, so they are moving. Well, they're at times going to collide with this molecule. And when they collide, they're going to pass on their momentum, and it's going to knock these in that direction. So say that two molecules happen to smack it in that direction, it's going to move that way. But a moment later, another molecule might be coming this way, which might knock it in that direction, and so on. So we can explain what Brown observed, that random jerky motion, by invoking the simple kinetic, I should add in there, kinetic molecular model to explain it. If we consider all these small air molecules or water molecules moving randomly, quickly, and colliding with this big smoke particle. And that helps explain what Brown observed. And it also shows that larger molecules can be moved around by much lighter, smaller molecules. The size doesn't matter so much, more the weight. So large mass can be knocked by smaller, less massive particles. I suppose a good analogy would be to think, if I got you all moving around randomly in the classroom, so you are moving around randomly, and I put a nice big coloured ball in the room. If you move randomly without thinking, occasionally you'd bump into the sides of the room, and sometimes you would hit this ball. And when you hit this ball, you're going to knock the ball off in a direction. But a moment later, someone else might hit the ball, and that will knock it off in another direction. If I could make you guys disappear, and we just look at that ball, well, we're going to see that moving with a random jerky motion, which is the Brownian motion. And this helped, as we say, prove the simple kinetic molecular model. Let's go back to our syllabus. Show an appreciation. So that first one there, show an appreciation that mass particles may move light particles. We've looked at that. Show an understanding of the random motion of particles in suspension as evidence for the kinetic molecular model. So, as we said, the smoke or the pollen moves randomly, and that shows that the smaller molecules are moving randomly as well. Describe the motion, sometimes known as Brownian motion, in terms of random molecular bombardment. We've also talked about that. Let's now have a look at the syllabus points here. Describe qualitatively. What does qualitative mean? Well, it's the opposite of quantitatively. And basically that's where you describe things using words. You don't need to use numbers. It's kind of more increase, decrease, rather than a mathematical sort of a formula. So, in terms of molecules, we need to refer to the molecules here. And we describe the effective pressure of a change of temperature at constant volume. So let's look at that one first. What does constant volume mean? Well, that means the cylinder, or whatever it's contained in, is closed and the walls can't stretch. So imagine just a metal can sealed all round. So nothing's going in or out. Let's put some molecules in here now of gas moving around randomly like that. Now, this one says what happens as the temperature, if you go back up, as a change of temperature at constant volume. So we've got constant V, constant volume, but we're going to heat it up. So here's my heat. Well, as you remember, hopefully, as you heat it up, what happens to the molecules? Well, they move faster, represented by this larger arrow. So what's going to happen to the pressure? Well, if they're moving faster, so higher temperature, they move faster because they have more kinetic energy, and therefore they collide more often, or you can say more times per second. Don't just say more, be specific. So more often or more times per second. And you need to tell me what you're colliding with. Well, more often with the container walls. Well, if they collide more often, and also they'll collide with more force, because they're moving faster, both of these are going to lead to a higher pressure. So as we increase the temperature, we increase the pressure. It might make sense if you can imagine heating up a closed cylinder. After a while, that cylinder can explode because the pressure gets so large. Let's now look at the other syllabus point, which asks us to explain, again, the effect on pressure by changing the volume, but this time the temperature is held constant. So what happens in this situation where we change the volume? So imagine a container like this. Might have, say, a piston. Let's make sure it's sealed at the sides, like that we can push in or pull out. The temperature is kept constant, so you could put this in a water bath to keep it constant, or use some other clever mechanism. But you've got to keep the temperature constant. So T is constant. Right, well, let's see what happens. As we compress this down, you can see the molecules are going to be forced into a smaller volume. Well, that means they've got less distance to travel before they hit the walls of the container. So once again, as the V or volume decreases, these molecules are going to collide more often. So molecules collide more often. Remember, nice and specific, more often with container walls. And again, when they're colliding more often with the container walls, that's going to lead to a higher pressure. So more collisions with the walls, more force over an area leads to more pressure. So we can see that if the temperature remains constant, and remember that's important, but we change the volume, we affect the pressure. And you notice that actually this is something in maths called an inverse relationship. As the volume went down, the pressure went up. We can also say the opposite is true. If the volume went larger, so we increased the volume, pulled the plunger out, the pressure would drop. An example would be inflating a balloon up and tying a knot. If I could stretch the walls out like this, well, the same number of molecules in here, but in a larger volume, so the pressure is going to drop down. What does this look like graphically? Well, you can do experiments to find out, but if you plot pressure against volume or volume against pressure, you get a nice inverse relationship like this. As one increases, the other decreases. And we say in maths this is inversely proportional. This leads to an interesting equation. Now remember, this is all when T is constant, because if you change the temperature, you change the pressure. It's not a fair test. We can't find this relationship. In fact, if the temperature increased, it would look something like this. It would be higher up here, but we don't need to worry about that too much. Just remember that the temperature is constant in this situation. And this leads to an important equation. Pressure times volume is equal to constant. What does that mean? Well, it means if you times the pressure and volume of a gas, so for example up here, if we times that by that value, you'd get the same answer as if you times that value by that value. This is a really useful equation. Now you can remember it like this, PV equals constant. Remember again, this is when T is constant. This only works. Or we can consider a change in a gas, and we can say P1V1 equals P2V2. So there's two forms of this equation. In the next video, I'm going to do some examples of using this equation and explain it in more detail. But I just want to show you where it came from, and you can do experiments to find that. Let's go back up to our syllabus to see where we are up to. So we've described qualitatively, that just means as one increases, what happens to the other one, how temperature and pressure are related. So remember, as the temperature went up, the pressure went up. And that was at constant volume. We've also explained how volume at constant temperature is affected. Remember, if volume goes up, then pressure goes down. They're inversely related. And this led to this awesome little equation, which I'm going to show you how to use in the next video. We'll also then talk about evaporation as well to finish off this topic on the simple kinetic molecular model.